Hello, Matvey. Do you hear me?
Yes, I hear you.
Yes.
Okay.
Kiminori,
Can you
we
hear
hear
me?
you too as well.
Okay, thank you. Can I
I'm
start?
chairman of this session. I'm Evgeny Tretyakov, and we start the second session of this third day of this conference. Let me remind you that we have two parts of this session. And we have, during the first session, we have two invited talk and two oral talk. And let me also remind you that we have 25 minutes for invited talk and 20 minutes for oral talk. And when you have, if you see yellow colored screen of my speech time, please please know that you have several minutes to finalize your talk. So we start with invited lecture of Professor Kiminori Maeda. Please, Kiminori, you have 25 minutes.
Thank you. Thank you for kind introduction. I'm Kiminori Maeda from Saito University. First of all, I'd like to say heartfelt thanks to the organizing committee and give me a chance to have this presentation. Okay. Just a moment. Okay. Before start some scientific thing, I want to show you some photographs because I met. Typically annually, I meet with Costia every year, and this one is probably my last visit to Novosibirsk for 60-year celebration of NSU at that time. And actually, before my leaving, we chat a lot at lunchtime. And actually, this one was my last met to Costia. And then 2019, we also had a spin chemistry meeting in St. Petersburg, and Kostya is here, and I was around here somewhere. But anyway, we met this conference, and also 2018. I can't find the photograph with Kostya, but we had a two continuous conference and summer school of the International Conference of the Spin Physics, Chemistry, and also the School for Young Scientists. 2017, and we met in the International Voivodesky Conference. I was just arrived, a bit tired, but we had a quite nice lunch time anyway. And also 2016, that was a very fruitful time. I invite Kostya twice in a year, and sometime we had some lecture series with Kostya and Chris Kay. And also 2016, we had a Kanto area spin chemistry meeting in Saitama University. That was quite nice opportunity to contact our student with Kostya and also the many invited speakers. And that we had a quite nice party in some hall. And after that, actually, we went to karaoke. And also next day after this meeting, we went to the classical town in Saitam Prefecture. This one is just costume of the some festival, Japanese festival, and we took. I got a quite nice photograph. Okay, that is just a memory, and also the. Actually, I published only one paper with Kostya. This is actually my first pure theoretical paper about the quite fundamental things of what is a spin selective chemical reaction. This is quite fundamental question, but at that moment there was some discussion about relationship between the spin selective chemical reaction and also the quantum measurement concept. Actually, we had a bit negative feeling about the quantum measurement concept, but and we agreed to each other and decided to publish some paper together. Okay, but I think this one was quite nice memory because this experience influenced my following research work very much. So I impressed very much the collaboration with Kostya. Okay, anyway, I'd like to thank Kostya. Okay, now today I'm also talking about a little theoretical, but we are now progressing the experiment as well. But title is reaction dynamics stimulated by static and oscillating magnetic field. But mainly I'm talking about oscillating magnetic field. So the actually last a few decades, actually in the laser chemistry people and try to control the chemical reaction using the some manipulation of the laser light or laser pulses. For example, this one is just a concept of the using some LCD filter and try to make some chopped optimize the chopped pulse and try to control the chemical reaction. But of course, manipulation of the laser field is quite complicated and sometimes very difficult. But in contrast, for the RF or microwave, it is very easy to manipulate. If we use some AWG, arbitrary wave generator, you can make such kind of, if you like to make such kind of oscillating magnetic field, you can make so easily. Just okay, so the concept is this kind of RF field using the using the AWG. How can we control the chemical reaction? This is one of the challenge. So I like to acknowledge some students and also the research assistant Professor Hiroki Nagashima, and also I got many advice from the Professor Sugawara. Now he is now in the quantum computing center in the Keio University. Okay, so the starting point is radical pair. Radical pair is, as already discussed in previous talks, actually radical pairs are very directly related with quantum, how to say, spintronics. Okay, for example, in the organic solar cell or organic LEDs, or such kind of system is a okay, some people call it a polaron pair, but this is the same as the radical pair. Radical pair concept is still working in such system as well. And also in the biology, photosynthetic system also produce a radical pair. And also recently, people are interested in some animal magnetic reception would be related with some radical pair formations. And so in general, actually, any redox system, if the electron transfers from the donor to acceptor, that produces anyway the radical pairs. Okay, in this sense, radical pairs are ubiquitous. So the previously, and there's some people, okay, in this case, the Morton had shown that some bird orientation is disrupted by some oscillating RF field. For example, this one is under some natural, RF noise condition. So orientation of the bird is disrupted. Okay, but in the case of if you shield this RF noise, okay, some test experiments suggesting that the bird is oriented to the direction of the north. This is the story at the springtime. So the bird were motivated to fly to north. In this case, they sense the some Earth magnetic field and trying to go to north. But this RF field, disrupt this orientation. Okay, but a similar thing is happening in the chemistry as well, of course, and that is called reaction yield detected magnetic resonance. If from the radical pair is produced from the singlet manifold of the radical of the state, and the initial radical pair state is in the singlet state, and the singlet state and the triplet state is mixed to each other coherently, typically from the hyperfine interaction. In this condition, if you illuminate a microwave or radio wave, some electron spin resonance causes some change of the reaction yield of the free radical, for example. So the monitoring the reaction yield and applied RF field and how to modulate the reaction yield is can be detected by the various spectroscopy, for example, optical absorption or light emission, or recently people is interested in the electric conductivity as well. But anyway, this one is all in the concept of the RIDMA, reaction is detected magnetic resonance. This technique is a little different from the directly observation of the microwave transition. Yeah. This technique is useful to see the relationship between the magnetic resonance phenomena and also some reaction dynamics. Okay, that is a Riedmer's concept. So based on this Riedmer's concept, so last Bird experiment can be suggested that that would be some kind of Riedmer phenomena would be happening in the Bird retina. That was the concept. But in the experimental room, okay, in the laboratory, we can just simply use some transient absorption detection. So for example, we pump the laser and produce a radical pair. Radical pair is probed by the probe beam and see the radio wave on and off. Okay, using that, we can see some Riedmer phenomena. Okay, again, the concept is same, but a bit split into some spin state of the radical pair. In this case, the radio wave pump the population from the STO mixed state to the T plus and T minus state. T plus and T minus state is a bit isolated from the ST0 mixed state. That is why the T plus and T minus state population is rescued from the recombination reaction process. Okay, that is the concept in the case of the singlet bond radical pair. But one of the questions is, if the radical pair have many hyperfine lines, for example, like that, in this case, single colored RF field is limited to modulate the chemical reaction. Of course, you can guess if we can use many RF field, okay, multicolor excitation, we can more efficiently change some chemical reaction feature. This is a quite simple and basic idea. So the arbitrary wave generator probably, or AWG based reaction control would be more efficient than the single color case. Okay, this is just a model calculation. If we use the AWG, it's more T plus T minus state, rescued state, the population is increased more monotonically. But in the case of the single color case, even if you keep the irradiation, some oscillation is happening and just limited to about 30% or something like that. So the concept is something like that. But the question is how to design the RF field. Okay, actually, basic concept, typical concept, popular thing is a grape technique. Okay, this one is if there are some, time-dependent RF field or something like that. Okay, we take into account we use some knob and change some amplitude. Okay, and change around, and how to reaction yield change. Yeah, but we need to do a quite iterative procedure. So this is a very hard job. But in contrast, actually for the reaction control, actually we need a rather rough technique, but more quick calculation technique we need. That is the global optimization. So global optimization, this is the local optimization. Grape is basically the global optimization. Okay. But we have chosen the local optimization method. Local optimization is just to directly try to get to approach to the target state. Okay, just monotonically increase the target probability and trying to, and based on that, we can design the RF field. Okay, this technique is rather suitable for the small number of quantum states, but good for spin systems. My feeling is, and also but the calculation is extremely faster calculation compared with the grape technique for rather complicated system. We can input some physical strategy. Okay, what pathway or which subensemble is more effectively react or something like that. We can input some physical strategy for the optimization process. And the very fine time resolution, very small time step is we can use. And of course, compared with the global optimization, probably not perfect, rather rough control, but it looks good enough for the reaction control in our calculations. So from that, we decide to model some relatively rather complicated systems. Especially, we tried some sub-ensemble selection and coherent controls. But today, I'm talking about the sub-ensemble selection and also the anisotropy, mainly talking about anisotropy selection techniques. Okay, so theory a little. This is only the formula. I'm basically the experimentalist, so I don't want to put so much complicated formula. But this one is just a simple. Okay, local optimization theory. We think about some duplication for the density matrix of the radical pair system. Okay, this one is just a spin Hamiltonian time evolution. Okay, and this one is just a oscillating field effect. Okay, this one is just a. And now, if we put the RF field UT is something like that. Actually, in this situation, this first derivative of the target probability. Okay, this one is a performance index of the target state. Okay, PI is the target state we like to go. Okay, and multiplied some weighting factor and summed up. In this case, this performance index monotonically increase if we input UT is something like that. So from that, if UT is like that, okay, anyway, we can approach to the target state. We input this UT value into here, okay, and solve the nonlinear equation. We can immediately get the future density matrix using this next step density matrix, and we can calculate the next RF field. Okay, this is just a step. From that, we can get the optimized RF field. And the key thing is this QI, this weighting factor. Actually, you can input this QI value arbitrarily, but this QI can give us we can input some physical strategy into this weighting factor. For example, if there are many sub-ensemble of the system, okay, total spin system is split into some sub-ensemble case. Okay, in this case, if you select this QI value for the favorite one, you put some positive value, and if you unfavorite one, if you can put some penalty value. So you can selectively make some transition for the system. Okay, but we can also have a different usage. Okay, if the individual spin state is mixing, all spin system is mixing each other. In this case, if you put this QI value, something like that, you can make some pathway of the quantum system. If you start from the starting point and go to P1, P2, P, and finally go to the Pn case, you can just input this kind of order of the QI value. You can make a pathway of the control of the spin system dynamics. But today I'm using this sub-ensemble control technique. Okay, for example, this is a quite simple example. If we have some radical pair of the benzophenone and also this PEG radical in the micellar system, for example. Okay, and the stick diagram of the EPR transition is something like that. In the case of this carbon, is carbon 13 case is something like that, pink one. But if this one is carbon 12, is a hyperfine structure is something like that. So putting the QI value for example, negative for the carbon 12 one, and also positive for the carbon 13 one, you can selectively accelerate the reaction of the carbon 13 rich molecule. Okay, this one suggesting some isotopic isotope selection method in the logical pair. Okay, so because all stick diagram can be considered as some ensemble of the logical pairs, and just pump the carbon-13 transition and accelerate recombination product. Okay, this is one of the method. But today the main topic is about Today the main topic is about our anisotropic system. We input an anisotropic logical pair. Okay, we put some anisotropic hyperfine interaction so far. Okay, and using that, and for example, if we don't select the transition, we pump everything. Okay, we pumped everything in this case. Okay, without our field radical pair decays, but we pump the radical pair and rescue to the T plus and T minus state. Okay, radical pair doesn't decay like that. If you use this kind of RF field, this one is designed RF field by the theory. Okay, in this case, radical pair or homogeneously pumped to the T plus and T minus state. So the radical pair population after with the RF field is homogeneously pumped and big population remained as a radical pair. But in the case of if we use a selective pumping, in this condition, okay, if the radical pair is parallel to the external magnetic field case, okay, this is the favorite, but perpendicular case with respect to the external magnetic field. External magnetic field direction is Z direction in this axis. And we put this kind of QI factor and just calculate the, calculate the time evolution. Okay, designed RF field is something like that. And you can see only the parallel component remained and the perpendicular component is dumped by the back electron transfer reaction. So, okay, this one is just a model calculation. And we can also do the opposite case. We put the negative value for parallel and positive value for the perpendicular case. Okay, calculation result is something like that. And also, we can also optimize this QI value using the some global concept, global optimization concept, and we can combine the local optimization and the global optimization, and we can get something good, better result of the anisotropic reaction controls. Okay, so you can see the. You can see the reaction control, anisotropic reaction control feature, just using the AWRF field. And if you look at the Fourier transform of the designed RF field, we can see that some strategy switching. In the case of the homogeneous free pumping, of course, resonance to isotropic partner radicals. Okay, this one is a case of the anisotropic radical and isotropic radical. In the short pulse provide a broad excitation of the partner radicals, mainly exciting the partner radical. But if we use a selective pumping, in this case, they change the calculation, change the strategy. Okay, we stop the pumping the partner radical and pumping some anisotropic resonance point of the anisotropic RF anisotropic resonance lines. Okay, so now we are moving to the experiment. Okay, now one thing is AWG is now the popular in the commercial machine, but very expensive anyway. So we built some new sample cell for transient absorption in the EPR. Okay, this one is already built. So and also nice thing is this transient absorption cell is quite compact, and actually you can put into the suitcase, and you can bring this machine to the equipment with the AWG, and we can measure some reaction control feature using this kind of designed RF field. And also in the case of the high field, we need to optimize the X and Y both channel, because the quadrature control is necessary. But this calculation is quite easy in the local optimization theory anyway. Okay. And another experiment plan is RF field, relatively lower field. We can use just RF, AWG based RF coil. Actually, now this is really building in our lab now. Already we had some preliminary result of the RIDMA with the 252 megahertz. And but so far this one is just a single color case. Now we can move to the AWG based reaction control now. Okay, okay, almost time. So I like to finish my talk. Okay, thank you very much for kind of attention.
Thank you very much, Kiminori. It's time for discussion. Any question? Any comments? I have one question. You said that you can control a recombination of pair of radicals containing different carbon isotopes.
Yes.
Is it practically applicable for separation of isotopes? Why you method?
I think no. This is just a collaboration with some Professor Wakasa and the Saito University. He has been studying a long time of the magnetoisotope related effect, and one of the idea is actually I don't know exactly this kind of RF-based isotope selection versus just a static magnetic field-based, magnetoisotope effect, which is better. I don't know, but my feeling is RF field method is rather more sophisticated, and because we can tune the EPR transition more precisely. I think in this sense probably rather possible, but we haven't actually previously we used just a pulse EPR based carbon-13 condensation. We have tried, but not so efficient so far. We are trying to do using the AWG based reaction control.
Thank you very much, dear Kiminori. Thank you for your lecture. And now let me introduce the next speaker of this session, Kazunobu Sato. He's from Osaka City University. The lecture is titled Spin Manipulation of Exchange Coupled by Radical Using Arbitrary Waveform Pulses Based on Pulsed-ESR Spectroscopy.
Thank you for your introduction. So let me share my screen. Can you see my screen?
Yes.
Okay.
Please, Kazunobu, please.
Okay. I'd like to start. First of all, thank you for giving me this chance to present, make presentations on this in this online meeting. And first of all, I have to say, Professor Konstantin Ivanov, who is one of my Russian colleagues and also one of the co-workers, and he passed away early this spring, this early spring. So I'd like to dedicate this talk to the memory of Kostya. So first, I'd like to start from the introduction of molecular spins as a spin qubit. And next, I'd like to talk about spin manipulation method for molecular spin by using the Pulsed-ESR technique, especially after waveform generator become available now. So such technology has a good advantage for spin manipulation. So in my talk, one of the topic is application of arbitrary waveform pulses using AWG. And such arbitrary waveform is applied to a stable spin system such as nitric oxide mixed system, which is a non-interacting system, and also weakly coupled biradical system. So here I show you typical electron spin qubit with extremely long decoherence time. Phosphorus atom in silicon has long decoherence time. The phosphorus atom, the relaxation time of the phosphorus atom is around sub-millisecond at room temperature. And the other famous example is NV center in diamond. NV minus has also long decoherence time at room temperature. The relaxation time of NV center even near the surface, the NV center has 45 microseconds. So recently, this NV center is attracting much attention because of the optical property with a long decoherence time and a highly polarized state. It is being considered as excellent quantum sensor. The long decoherence time of phosphorus atom or NV center are coming from the property of hard materials. When we look for the molecular spin candidates as a qubit, there are several molecular spin systems with long decoherence time. Famous examples are shown here. Nitrogen doped C60 has 250 microseconds at 107 Kelvin in the carbon disulfide solution. And Winpenny and co-workers reported of heterometallic foil complex, which consists of chromium and nickel transition metal ions. This complex has a 2.2 microsecond in the case of per-deuterated complex. And vanadium complex have also very long decoherence time. This relaxation time is around sub-millimeter or several microseconds. And one of the carbon-centered radical, this so-called Finland torture radical. The torture radical has 11 microsecond at room temperature. So they are all good candidates for the electron spin qubits in molecules. Not only single electron spin system, but also multi-electron system applicable to quantum information processing. So Jenkins and co-workers reported a high spin state of gadolinium metal ion. This is a single crystal ESR spectrum of this compound. They observed a transient. So, and characterize the spin dynamics of this compound. And by observing nutation phenomena and Rabi oscillations, he shows that it's possible to control each transient by microwave. So this is an extension of the spin space from qubit to spin state to many spin states. In other words, the extension from qubit to qubit to qubit. Qubit means a quantum d-dimensional bit. And also heterobimetallic complex is also good models for spin qubit system, especially 2-qubit system. Aromi and co-workers developed such complexes and discussed the effectiveness of this complex as a spin qubit. When the interaction between metal ions, this is a good model for two-qubit system. When constructing qubit arrays using the molecular spin candidates, we'll be able to consider and design the promising spin system for appropriating for quantum information or computing processing. Many years ago, arrays of endohedral fluorines and p-pod nanotube have been proposed for quantum qubit array. However, this proposal is a quite challenging issue. And very recently, around 5 years ago, Fernandez and co-workers reported the rotaxanes with foil complexes. This is something like a manufacturing of the spin qubit network. This is good models for small qubit system. And we have studied triple-stranded metal helicate and tandem arrays of radicals on DNA as models for small qubit arrays. This experimental results shows some indicates that some difficulties for technological difficulty for spin manipulation. Among them, one of the good models for two-qubit system is a weakly coupled biradicals. Here I show you some gate operation for two-electron spin qubit. And this is weakly coupled biradical. This compound is diluted in the diamagnetic host single crystal. Crystal structure shows the spin distance between nitroxide pulse around 20 angstrom. This distance corresponds to the spin dipole coupling of around 10 megahertz. So this is a single crystal Eldor experiment. This shows single crystal Eldor experiment. The signal shows angular dependent, and by rotating the single crystals, we can change the dipolar coupling like this. So this compound is applied to demonstrate control knot operation for electron spin qubit. This is a single crystal ESR spectrum of this compound. In this direction, the spectrum shows a small splitting. This splitting is due to a spin dipolar coupling. It means we can easily excite single transition by applied microwave pulse. This is a mutation phenomena of this single transition. And spectrum shows the Rabi oscillation. And in this case, a 200 nanosecond rectangular pulse corresponds to 180 pulse. So 200 nanosecond rectangular pulse plays a role of control knot operation for this specific spin transition. And this C0 operation is is given by this picture. And this C0 operation is figured out by simple density matrix map. In this system, spin system for 16-dimensional. So this control knot is given by this density map, this matrix map. And also the same operation has been done for this different weakly coupled biradical. In this case, the spin dipole coupling are a bit greater than the previous one. So in this case, we can reduce the operation time 30% by applying much stronger microwave pulse. How we can reduce the time is molecular dependent. So molecular design for useful quantum gate is very important from the viewpoint of the spin coupling. So molecular spins are promising candidates for qubit. It is one of molecular spin application. It's quite challenging. There are a lot of issues for applying the molecular spin system to quantum information processing. We have to satisfy the requirement for spin qubit. One is an issue for the molecular materials. We have to consider the molecular optimization as a spin qubit. And there we have to consider the many addressable qubit with long decoherence time. This is quite challenging issue in the materials science. Another issue is oriented to technology. We have to need to develop the spin technology for spin manipulation. We have already a lot of Pulsed-ESR technique and methodology. In order to such methodology, we have to much more precise technology for spin manipulation. So AWG based ESR is has one of the advantages for spin manipulations, and especially arbitrary waveform is applied for precise spin manipulation and optimal control for all the spin state. Application of the arbitrary waveform pulse, such as gray pulse, will be one of is one of the optimal control of electron spin. Gray pulse approach is to construction of optimized arbitrary waveform pulses for performing desired unitary operations. And here I show you a calculated gray pulse. And this gray pulse this is optimized for creating a superposition state of electron spin with of resonance conditions. This pulse corresponds to a pi/2 pulse with some of resonance conditions. Such waveform is calculated by a numerical optimization, and this pulse is applied to simple molecular single spin system like a DPPH. This is a field swept FTESR spectrum of DPPH by applying this gray pulse. Field spec, this profile, FT-ESR profile, is explained by the power spectrum of this gray pulse. In this case, our arbitrary waveform works as expected. So here we consider the optimal path design for exciting of resonance transition of single spin system. On resonance condition, the story is very simple. Pi/2 pulse was given by rectangle pulse with pulse length Tp. And this Tp depends on the irradiation field strength B1. And when moving away from the on resonance condition, we need to consider the offset effect to make a gray pulse. For the Pi/2 pulse under the resonance conditions, unitary operations for given by exponential operator. And density matrix of the target state is given by this equation. So we have calculated optimal pulse sequences with fixed pulse length to reproduce the target state. Some calculations, calculated pulse sequences are shown here. This gray pulse consists of 2 rectangle pulse, and this one consists of 10 pulses, and this one consists of 20 rectangle pulses. The pulse sequence was obtained by the optimization of the unitary operator from the initial state to the final target state. 2 colored pulses indicate the phase rotated quadrature phases, and some spin trajectories are given for the obtained pulse sequences. 2 pulses sequence correspond to a purple line, and 20 the gray pulse consists of 20 pulses correspond to a red line. And the red line is approaching to the almost target state. So it means this red line has high fidelity and small distances. In order to evaluate effectiveness of the pulse sequence, we will introduce this fidelity and distance. And in the case of the 2 spin system, the situation becomes complicated. It is tough to find the optimal short pulse sequences. We consider the fidelity of the optimal pulse for the site selective excitation in the 2 spin system. And these plot show the fidelity and distance of the simple rectangle Pi/2 pulse at the position field position A and B. And at the position field position A, where is the resonance position of spin 1? When spin 1 is selectively excited, the highest fidelity for the rectangle pulse is found at the irradiation strength near the 10 megahertz. So this is it is very close to the exchange interaction assumed. Then the distance takes a small value. So in this case, for the rectangular pulse, around this area is optimal pulse for selective excitation. On the other hand, at the field position B, which is the resonance position of spin 2, in this case, we cannot find the optimal pulse. So in this case, there is no effective pulse for selective excitation of spin 1 at the field position B, and there are limitations for rectangular pulse. And in order to avoid such limitations, we consider the gray pulse. And I show the fidelity and distance of the gray pulse is calculated. Both fidelity and distance depend on the total pulse length and number of steps or number of pulses in the sequences. Generally speaking, the longer gray pulse has high fidelity and small distances. And increasing number of pulses improves the fidelity and the distance of the grape. And this is a spin trajectory. Each spin trajectory, this trajectory shows spin trajectory for spin 1 and 2 when applying this type of gray pulse. Spin 1 go to the final state. On the other hand, spin 2 is back to the initial state after the gray pulse. So this is this means a selective excitation of spin 1. So here I show general requirements for an optimal pulse for site selective excitation with high fidelity in the isotropic two-spin system. And red area indicates a high fidelity area. The area depends on the mounted parameters, and especially J and delta G, as well as irradiation microwave field. Apparently, a critical length exists for selective pulses. It shows the effective optimal pulse are available when the pulse length is longer than the critical pulse length. In order to demonstrate the selective excitation using gray approach, we have applied the optimal pulse to the stable mixed spin system, which consists of nitrogen-14 nitric oxide and nitrogen-15 nitric oxide radicals. This is observed FT-ESR spectrum. 3 transitions are attributed to nitrogen-14 nitric oxide, and the 2 lines are coming from nitrogen-15 nitric oxide radical. And for the spin system, I have calculated the optimum pulse for single transition excitation. In this slide, I show a calculated optimal pulse for single excitation. And this is a calculated fidelity. The calculation shows a high fidelity for each transition. When applying these gray pulse, we can observe these spectra each spectra has a single transition. So these results shows this gray path works as expected. Now, I'd like to present application of optimal path weakly coupled biradicals. In order to perform optimal path experiments, we design and synthesize weakly coupled biradicals, which consist of torchil radical and nitroxide radical. In this case, biradical is coupled by phenylene linker. This one is two radical sites are coupled by naphthalene linker. After characterization of the spin system, applying the multiplex ESR spectroscopy, we have applied arbitrary waveform paths to the system in order to modify the spectral modification of the FT-ESR spectrum. Here I show you a CW-ESR spectrum, this compound, and naphthalene bridged biradical system. And this is an expanded spectrum, and this is Q-band spectrum. And this splitting, two signals to assigned to the torchil radical side. And this splitting is coming from exchange interaction. And when changing the microwave frequency, this transition shift higher field. So in this spectrum, when we change the microwave frequency, this splitting doesn't change. So this splitting is independent of the microwave frequency. So this is coming from interaction between the spins. In this case, this splitting from this splitting, the exchange coupling is 3.7 megahertz for this biradical. And this is the results for this compound, phenylene bridged biradicals. In this case, the splitting is a little bit greater than the previous one. Then the exchange interaction, we determine the exchange interaction is around 6.4 megahertz for this compound. And this is quite reasonable. The interaction naphthalene coupled system is smaller than the exchange interaction of this compound is smaller than that of the phenylene coupled biradicals. For this biradical system, we consider the signal intensity modification by applying arbitrary waveform paths. This slide shows various FT-ESR spectra of phenylene coupled biradicals. A shows a theoretical spectrum, and B is observed spectrum by applying rectangle paths with very short rectangle paths. In this spectrum, we fail to observe the weak signal due to the nitrogen oxide, the spin, because of the weak intensity. In order to observe small signals, we try to apply various waveform pulses for these radicals. This shows spectrum observe the combination pulse of 3 microwave frequencies. the microwave pulses are applied to selectively excite all the nitro oxide radical transition. D shows a spectrum by applying a square root chap excitation pulse with pulse length at 400 nanoseconds. And the frequency was swept from -80 to +80 megahertz. E and F showed spectra observed by gray pulse given here. And the maximum microwave field was 20 megahertz. The observed spectra indicates that a certain amplification of weak signal was observed by our designed arbitrary waveform pulses. We will be able to improve the amplification by modified waveform pulse. This shows the case of a naphthalene bridged compound biradical. Similar results are obtained by applying various pulse waveform pulses. And this exchange interaction is smaller than the phenylene bridged biradicals. In this case, it seems the signal amplification works rather than the previous case, and after phenylene bridged case. So probably some advantage for this compound to manipulate spins, because spin coupling is a little bit small. It is not precise result. However, the difference between calculated pulse shape are clearly shown in the spectrum, indicating the effect of gray pulse. Finally, I'd like to conclude my talk. Today, I showed Pulsed-ESR technology with arbitrary waveform pulse has been applied to stable organic spin system, and I showed some experimental results for selective excitation by gray pulse, and such technology has been applied to weakly coupled biological system. And finally, the AWG-based ESR technology enable us to control quantum state of spin system. Thank you for your kind attention.
Thank you, Kazunobu, for your nice lecture. Unfortunately, we are out of our schedule. If somebody wants to ask one short question, please. Okay, Kiminori, please.
Thank you very much. Very wonderful talk. And I want to ask you that how much the difference of the T1 and T2 is a problem for the optimization of the microwave field by on the, how to say, gray pulses.
Look, in my case, the gray pulses apply to solution system, so I don't take care of the difference of T1 and T2.
Okay.
But however, the relaxation time should be longer than the operation time.
But in the case of the solid state, is it possible to optimize our field, take into account the difference of T1, T2? But this is unitary transformation. So I'm a bit wondering that depend on the initial condition, a little problem of the T1 and T2 the difference.
Yeah, in the solid case, generally speaking, the T1 is very long, over millisecond order. On the other hand, the T2 is less than can usually
Yeah.
for the nitroxide radical.
Uh-huh.
So pulse design great pulse length is very important. Pulse length is less than the phase memory time.
Okay.
So usually we use for the pulse length is around 200 to 100 nanosecond pulse length. It is less than the phase memory time.
Thank you very much.
Thank you, Kazunobu. Thank you very much.
Thank you very
Let
much.
me now introduce the next speaker of our session, Sergey Norkov from Razovayev Institute of Organometallic Chemistry. The lecture is titled Annulation of 1,3 DTO ring, phase wave for versatile functionalization of o-Quinones. Please, Sergey, you have 20 minutes.
Hello, everyone, and thank you for introduction. One second, please. Okay. In the field of organic and coordination chemistry, the last 2 decades have witnessed increasing interest for the design of molecular devices, molecular switches, and molecular conductors. Electron donors and electron acceptor, as well as their hybrids, are promising objects for the creation of molecular materials. Controlling redox states of a molecule is one of the ways to control of the electronic and spin states of this molecule. Derivatives of tetracylcovalent and 1,3-dicyl-2-ylidene are known as donor fragments, so they attract attention for the synthesis of different systems: donor acceptor, donor, and aza. Planar structure and sulfur-sulfur intermolecular interaction, intermolecular contacts allow for organizing strong intermolecular interaction. One of the main direction in this field is functionalization of 1,3-dicyl-2-ylidenes with various groups and fragments capable to coordinate to transition metal atoms and to expand the range of redox properties. Some compounds based on derivatives of 1,3-dicyl-2-ylidenes, which can be used as electrodes of accumulator, chemiluminescent sensors, or molecular switches, have already been reported. O-Quinones are both well-studied and promising redox-active chelating ligand. Combination of o-benzoquinone with 1,3-dicyl-2-ylidenes is a way for introducing functional groups bearing either fragments capable for coordination of free radicals and for preparing molecules with advantageous redox-active properties. Functionalized o-Quinones have prospect for use as building blocks in the construction of polyspin ordered systems with controlled switching between different magnetic states. Previously, it was shown that some binuclear complexes with tetracylcovalent functionalized the o-Quinone exhibit single molecule magnetic behavior and have unique luminescence properties. The right topology for the device might be provided due to presence of the 2 coordination sites and the termini of bridging ligand. The aim of the research at the synthesis of novel o-Quinones annulated with 1,3-dicyl-2-ylidene fragment and study their properties. Reaction between 4,5-dichloro-3-segregated butyl o-benzoquinone and various derivatives of gem-dicylate was chosen as a functionalization method. This method allows us to synthesize compounds which are not accessible by reaction involving 3-segregated butyl o-benzoquinone. O-Quinones annulated with 1,3-dicyl-2-ylidene were synthesized in a 2-step reaction. At the first stage, CH acids were deprotonated using a strong base and then were allowed to react with carbon disulfide to give corresponding gem-dicylate derivatives. At the second stage, 4,5-dichloro-3-segregated butyl o-benzoquinone was added. and the desired reaction product formed. Compound 15th was prepared via reaction of compound 1 and sodium tritiocarbonate in an dimethyl formamide. According to X-ray diffraction analysis of compound 15th, carbonyl groups are located out of the plane of the molecule due to steric hindrance of the Z-butyl substituent. Like other sterically hinded o-Quinone, they can undergo to step-by-step one electron reduction in solution, being treated with an alkali metal or thallium amalgam yielding semiquinonate and catecholate species respectively. Semiquinonate will be also generated in solution by the reaction with demanganese decarbonyl. EPR spectra parameters for free radical semiquinonate forms are shown in the table. The exact values of splitting constant were calculated during the simulation of the experimental EPR spectra. Isotropic G factors are similar to those observed for other metal complexes in sterically handed o-Quinone. Compound 15th exhibit 2 subsequent 1 electron reversible reduction waves. That is typical of sterically handed o-Quinones. Annihilation of substituted 1,3-dicyl fragment makes this quinone more strong oxidant than 3-cyclic-butyl autobenzoquinone. The compound 15th is significant interest as a potential precursor for synthesis of tetraacyl equivalent and 1,3-dicyl 2-ylidine derivatives. According to electrochemistry data, replacement of the sulfur atom by a malone-neutral fragment makes the quinone 16 a stronger electron acceptor. In contrast to compound 15th, third reduction potential is observed. We suggest that this potential leads to the reduction of a malone-neutral fragment. However, in the EPR spectra, we didn't observe such stages of reduction in reaction with alkali metal. Due to acceptance, compound is gradually reduced to catechol in the presence of air. According to X-ray diffractometry data, the fragment including 1,3-dicyl cycle is almost planar, as well the malone-neutral unit. The 6-membered o-Quinone ring is distorted due to steric repulsion of Z-butyl groups with carbonyl as well as from sulfur of annihilated 1,3-dicyl cycle. During isolation of compound 17-AD, the byproduct 22-AD were also isolated and characterized. In 17-AD, both carbonyl oxygens of acetyl acetonate unit are directed towards the 1,3-dicyl ring, and the sulfur oxygen interatomic distance is 2.56 angstrom. Such orientation of oxy group is typical for related systems. Since the systems is conjugated, the EPR spectroscopy study reveals spin density localized on the methyl groups of the acetyl acetonate fragment. According to electrochemistry data, first reduction potential of the o-Quinone depends on the nature of the substituent of the beta-decatonate fragment. When methyl fragment is changed to alkoxy group, a cathodic shift of the reduction potential quinone-syn-quinone by 0.1 volt. Lowering acceptability of the autobenzoquinone is observed. The second product of the reaction, 22-AD, contains annihilated thiet cycle. Benzothiate are known to highly reactive and unstable compounds. However, o-Quinones 22-AD demonstrate high stability in air at room temperature, both in the solid states and in solution. Compound constitute first example of structurally characterized benzothiate groups. In the IPR spectra, spin density of the methyl groups of the acetyl fragment is also observed, but the value of hyperfine splitting constant on these methyl groups is less because there is no conjugation with the o-Quinone ring. The compound 22A demonstrates two subsequent one electron irreversible reduction waves, which is typical to sterically binded o-Quinone. This no reduction of this functional group to -2 electron volt due to the absence of conjugation with the acetyl fragment. When sodium mesylate was used for the preparation derivatives of 1,3-dicyl-2-ylidines based on melanates, product 23 was isolated in quantitative field. According to X-ray diffraction analysis, the carbon atom in the 1,3-dicyl ring is sp3 hybridized, thus affecting acceptor properties. This o-Quinone is stronger donor than 3-segregated butyl o-benzoquinone, and its reduction potential value is close to those found in alkoxy derivatives of benzoquinone. Noteworthy in the case of sodium hexafluoroacetylacetonate, 1,3-dicyl-2-ylidine product could not be obtained. After treatment of sodium hexafluoroacetylacetonate with carbon disulfide, the reaction mixture changes is in color, like in other cases. However, after subsequent addition of o-benzoquinone, no color change is observed. X-ray quality crystal were ground from pentane. X-ray diffraction study reveals that in the course of the reaction, co-crystallized of parent o-Quinone 1 and sodium hexafluoroacetone. Then a chain coordination polymer is formed. According to NMR spectroscopy data, adduct 24 is in methanol solution, exists as stoichiometric mixture of compound 1 and sodium hexafluoroacetone. So that adduct 24 forms in a crystal phase only. Product 19 contains a parquinanoid fragment and the periphery of the molecule, which according to X-ray data is conjugated with a p-electronic system of o-Quinanoid fragment. The double bond between 1,3-dicyl and the peripheral 6-membered ring provides a rigid and almost planar structure for the molecule of 19s. Very similar structure was observed for the annihilated triad o-Quinone, paraphenylene, extended tetracyl-equivalent o-Quinone. Since compound 19 has conjugated systems, the reduction of o-benzoquinone to semiquinonate can be illustrated with two resonance forms. So values of reduction potential could hardly be assigned to the reduction of certain fragment. Among popular objects of investigation in the field of complexes possessing magnetic conducting properties, there is a 1,3-dicyl-2-cyan 4,5-dicyllate fragment and its derivatives. Thorsten Mies has reported on the preparation of naphthoquinone Annulated is the 1,3 dicyl to cyan for 5 dicylate fragment in a 65% yield. Compound 20 and 21 were prepared in a similar way and characterized by NMR, infrared spectroscopy, and X-ray diffraction analysis. According to X-ray data, both 6-membered rings have strong intermolecular deviation from the plane due to steric repulsion of 10 butyl groups from the sulfur atoms of the deuterium ring. In the derivatives of 1,3 dicyl to ilidance, the distance between sulfur atoms is in the ring is 2.9 angstrom, while in this compound the bound distance is 3.17 angstrom, leading to a strained molecule. The angle in the deuterium cycle is about 58 degrees. Compound 20 and 21 are unstable and decompose. According to electrochemistry for both 20 and 21, the first reduction potential values are equal. Study of synthesized o-Quinones by means of ultraviolet and visible spectrometry demonstrate that their optical characteristics are typical to those of sterically kinded o-Quinone. All these o-Quinone exhibit two white bands in the ultraviolet visible spectra in the 380 to 400 nanometers and 520 to 600 nanometers region, corresponding to PP and NP transition respectively. The extinction coefficient by 5 to 7 times, in some cases by an order of magnitude, higher than the value previous recorded for the photobenzoquinones. Noteworthy photodecarbonylation reaction of photobenzoquinones occurs not only under ultraviolet irradiation, but also under visible light irradiation condition. Introducing sulfur-containing substituents into the 4 and 5 position of 3-secreted butyl substituted o-Quinones increases the rate of photodestruction by more than 2 orders of magnitude. Such high photodecarbonylation tendency of prepared o-Quinones is a negative factor which should be kept in mind when creating the stable system based on this legend. In summary, a novel effective method of synthesized resegregated butyl benzoquinone annulated at 4-5 position with 2 substituted 1,3 dicyl ring have been elaborated, and series of new o-Quinone possessing additional coordination sites at the periphery of the molecule have been prepared. Thank you for your attention.
Thank you very much, Sergey, for your interesting lecture. Now we have time for discussion and question. Who would like to ask question? I have one question. Oh, okay, Artyom, please.
Thank you, Sergey, for your presentation. I want to ask a question about EPR data. For some of the salts, you have a G factor values below 2. How to explain such low values?
Thank you for your question. And can you repeat question more slowly?
The G factor values are below 2. How to explain these values? typical values of G factor for
I see. That's true. And now I can't answer on your question honestly, because we didn't think about it.
Okay, thank you.
Okay, could you please? Okay, Fabrice, please.
Yes, thank you, Sergey, for your talk. If I understood well, on the slide 13, and you said that the two compounds, so the compound 20 and 21, are not stable, right?
Yes.
Do you know what are the products of decomposition?
We tried analyzed in what compounds we get after decomposition, but at now we didn't know what we get after decomposition. I can answer that in NMR spectra we get single peak at single peak, and this compound are symmetry. But else answer on your question at now I can't.
Okay. Thank you. If I can, I have a second question directly related to the first one. So you say that it's not stable, but it's not stable in air, or what is the problem? The air, the temperature, or in solution, solid state? I mean,
compound 2021 stable at low temperature in solid state.
okay.
Not in solution in low temperature, room temperature, and we think it's they decompose because in their structure it's very distorted repulsion in intermolecule.
Okay. Okay. Thank you, Sergey. Thank you.
Sergey, I have a last question. On slide 11, you have shown that sodium salt of hexafluoroacetylacetoate does not react with carbon disulfide. Did you use more rigid 11? Slide number 11. Yes. So sodium salt of hexafluoroacetylacetoate does not react with carbon disulfide. Did you try to use a more rigid condition for this reaction?
We tried we tried to react in different solvents in dimethylformamide, tetrahydrofuran, and other, but results it's one.
What about autoclave? Reaction in some autoclave?
We tried provide synthesis in NMR tube, but hexafluoroacetylacetone did not react in carbon disulfide in other condition, and we tried different ways and condition, but not result yet.
Okay, I see. Thank you, Sergey, again for your lecture. Thank you. Let me now introduce the next and last speaker of this part of this session, Igor Shcherbakov. He's from Southern Federal University The lecture is titled Hexacoordinated Cobalt Compounds with High Magnetic Anisotropy, Molecular Design, Synthesis, and Quantum Chemical Modeling. Please, Igor, you have 20 minutes.
Thank you, Evgeny, for introduction. Do you hear me?
Yes, yes.
And what about the presentation?
Yes, we see your presentation, so everything is okay.
Thank you. First of all, I want to thank the organizing committee for this possibility to have a talk at this very respected conference. And of course, I cannot talk about this special day, which is devoted to the memory of the scientist, Konstantin Ivanov. I didn't know him personally. But of course, everybody should agree that this pandemic situation, which influenced all the aspects of our lives all over the world, causing the problems, a lot of limitations, and everybody are impacted by this disease. But of course, not any limitations and problems can be compared with the human life. This COVID disease is taking life, and it's taking lives of the common people and the people who are known and who have great potential to have to do much things which will contribute to the future. And of course, every human is important, but if we're talking about such people, such human as Konstantin, of course, the griefs are multiplied and power up by the number of the colleagues, friends, relatives who knew him, who collaborate with him, and who, of course, will bear his memory in their minds. I'm sure he will be remembered by everybody. Now I'm going to my talk. This work was done in the collaboration of Southern Federal University, our chemical faculty, and the Institute of the Problems of Chemical Physics from Chernogolovka, Sergey Aldoshin's academician Aldoshin's group. First of all, magnetic anisotropy is the dependence of the substance response to the applied magnetic field upon the orientation in it. On the molecular level, this dependence is realized in the zero field splitting. This is the number of the interactions which are lifting the degeneracy of the states with different projections of the momentum. And it can be mathematically expressed with the Hamiltonian, which is called the zero field splitting Hamiltonian. Just a second, I'll take the pointer. And this D tensor is a 9-member matrix, which is after diagonalization, and due to traceless nature, can be expressed in 2 parameters, the axial parameter D and the rhombic or transverse parameter E. Depending on the sign of the axial parameter, the sequence of the stability of the levels is reversed. For D negative, we have the example of easy axis magnetization system. The levels with the highest projection are stabilized. If D is positive, we have the easy plane case, and in this case, the levels with the less value of projection are stabilized. This diagram is for the spin system with 3 unpaired electrons, which will be discussed in the talk. The anisotropy is very important for many properties of the compounds, but it is in the focus, of course, because of the searching for molecular magnets, the systems which can store the magnetization within one molecule or even within the single ion. If we have the easy access situation with stabilized states with the highest modulus of MS, we have the double well potential, the height of the barrier separating the states with the opposite sign of the projection is proportional to the d value and the square of this total spin ground state. If we start from the situation when the both directions of projections are populated unequally, then after the application of the external magnetic field due to the Zeeman interaction, we have the lifting of the degeneracy and the system goes to the one projection of this. After the field is off, this population is trapped, and if we consider that the relaxation processes, which are many, Orbach, quantum tunneling, thermally assisted quantum tunneling, Raman, and so on, if these processes are enough slow, then we have the stable system, and the time which system is keeping the magnetization can be just, as now seen, considerable. The era of the searching of the molecular magnets started with the 3D metals. This is the epochal manganese 12 cluster. But very rapidly, it was recognized that the rise of the spin of the ground state is not the correct way for the molecules with the high blocking temperatures. And Waldman shown in his work in 2007 that the XL anisotropy parameter is approximately reverse proportional to the square of the total spin. And so the influence of the rising of the spin in spite of this square dependence is not the good way for searching. And it started the investigations, the research faced to the few or even single ion systems, but with high magnetic anisotropy. This is the best results there were obtained for the lanthanides, which is easily explained by the huge spin orbit coupling in these ions. The first Ishikawa was the pioneering work in 2003, and in just 15 years, very promising results were obtained with the barrier reversible up to 1050 reverse centimeters and blocking temperature about 80 kelvins. But the interest in the 3D SIMs or single molecule magnets is retaining. And here in this family of the complexes, the Cobalt is the metal of choice, and due to Kramer's nature of this ion. And among these complexes, the best results are shown by the two coordinate complexes, where also rather high effective barrier is registered up to now. This is the the best known up to now. This is very close to 500 reverse centimeters. Of course, the complexes with two coordinated metal is not enough stable, and more convenient coordination numbers are exploited for obtaining the single ion magnets. And here we have, for example, for the 6 coordinate complexes, the negative d values, rather high values, are obtained for the complexes with the trigonal prismatic structure. This is the work of Professor Novikov's group and the work of the Professor Yao. Here we have the effective barriers up to 200 centimeters and rather high magnetic anisotropy. So if we compare the different coordination polyhedra and compare the atomic orbitals splitting, we can see that why the trigonal prismatic structure is the most good for obtaining the negative large d values. The components of the d tensor, can be calculated from this rather complicated formula, which is the sum over the excited states and the elements of the matrix of the momentum projection of the orbital operator. The most important conclusion from this formula is the following: the largest contributions are from the orbitals which are involved in the first excitations, and if these orbitals are of the same ML value of the same, then, well, for example, dxy, dx squared, and the pair dxz and dyz, then the contribution from this excitation will be negative, which is good. And if the orbitals are of different ML value, modulus ML value, then the contribution will be positive. And the second is the reverse proportionality of the contribution to the energy of the excitation. So the first excitations contribute the most to the corresponding d value. In case of the trigonal bipyramid, if we look at these 3 levels, we see that the degeneracy of these orbitals should lead to the very small energy excitations. And so this will be the contributions, the most of the largest contribution from there. And the both orbitals here, dxy and dx squared minus y squared, are of the same ML sign. That's why the contribution is large and negative. So what can we conclude from these observations? Obvious that the total shape of the pyramid can be expressed as the cylindrical. And in this case, the z direction is the z-axis is going through this axis of the cylinder. This leads to the easiness of the crystal field along the z directions and stabilization of this state. And leaving the two orbitals with 3 electrons, they generate. So this is only these 3 orbitals are important for making the complexes with D7 configuration, and with D7 configuration, so the Cobalt 2 complexes. What we propose to do, we propose the total design in such a way. So to make the axis free of the crystal field, we need to point this C2 axis along the bond, not to the donor atom, but along the bond. And the next step is to make this structure more distorted from the octahedral one. This is achieved due to following. If we take these 5-membered rings, then the biting angles lie in the range 70 to 75 degrees. So 3 of them make somehow 210, 220. And just leaving the angle XY, X1, Cobalt X1, very wide, just allowing the angle between A, Cobalt A, also to deviate from the 180 degrees, making some kind of an arrow. And this is the total design of these complexes, and it's very variable because we can easily obtain complex ligands with different X, with different X1, and with different A's. So we choose for the testing of this system the very simple ligand. This is the bis hydrazone of diacetyl and 4,6-dimethyl hydrazine-pyrimidine, easily obtaining ligand, and we have tried for these 2 salts. This is the isothiocyanate and the chloride one. They are described in our publications, which are downloaded. What we obtained, this is the X-ray structure, and this is the coordination angle. Here we see that we can choose this as the plane, and the C2 axis is going along the center of the CC bond, and just the Z squared orbital along this axis must be more free and will go down with the d orbitals. Here we see that the angle between the terminating nitrogen atoms of the ligand and 3-cobalt-1 is very wide. It's 146, and the angle between chloride atoms, chloride, cobalt, chloride, is nearly the same. So this N3 and 8 and 2 chlorides form nearly the plane. Yes, and so this is the kind of the double-headed pyramid. Yes, it can be just named so. Or if we remember the talk of Norkov, it is the rabbit. Yes, with his ears. The substitution to the coordination angle. This is the mix of two pictures. If we go to the shape analysis, this is the continuous measure of the distortion of the polyhedron. We can see that the deviation of the angle of the structure from the octahedral one is 11. while 0 value is corresponding to the ideal structure. So we go far away from the octahedral, and this parameter for the tetragonal for the trigonal pyramid is only 6. In case of the isothianate, we have even closer structure to the ideal pyramid, which is good for the distribution of the AUs and so for the desired properties. The length of the bonds in the structure is the following, that those who are going to the N1 and N5 are shorter, much shorter, and to N3 and 8 are longer. This is due to the rigidness of the ligand. Its geometry dictates this type of the distortion. Now going to the magnetic properties. The direct current magnetic field for the chloride anion is shown here. We exploited the Griffith-Hamiltonian because of the low excitation first energy, but the spin Hamiltonian of more traditional one to derive the d value gives the same quality approximation of the experimental data. And here we see the d value is rather high, going up to 80 reverse centimeters. But the drawback of the structure is a rather big anti-ferromagnetic magnetic field, which gives rise to the fast relaxation processes. This is due to the dimers, which are formed with the participation of the chloride and anions, and also one pathway was found due to the solvate water molecules which exist in the crystalline structure. So it is bad. That's why the zero field alternating currents in magnetic field doesn't reveal any response from the substance. So only within the applied field up to 1/10 of Tesla, the signal do appear. And this is so we can say about the field-induced SIM properties of this compound. Very interestingly, that in the higher fields, the mechanism which is observed at 100 is followed by one more very slow mechanism of relaxation, which is disappeared with the heating of the system. So this is very interesting case of slow relaxation, because this is maximum is less than 1 Hertz in value. In the article, we explain this by the existence of the intermolecular interactions and formation of the magnetic domains, which are disappearing when cooling, when heating up the system. But the talk which was given on Monday by Oksana Kopak showed that this maximum is retained when the substance is absorbed on the ferromagnetic particles. And so if we are going from the solid sample to the solution, the intermolecular connections must be broken. But provided maybe on the surface they are formed again. So this the nature of this maximum is still under discussion, and the results of Chernogolovka's group gives a new questions to this substance. The calculations were done within the ORCA and MolCAS-8 programs and give rather good agreement. The sign is the same, and the prediction of the value is something in between of these methods. Atomic ab initio ligand field theory diagram is shown on this slide for the compound with chloride anions, and the classification of the di orbitals are given in this molecular frame. This frame is coinciding with the D frame, so it is the directions of the anisotropy axes in this compound. Here we see that the d orbitals are very close to each other, which are 3 of them, and these 2 levels are quasi-degenerate, just giving the big contribution into the calculated XLD parameter. And here also we can see that in both states, the orbitals with the same ML value are contributing. That's why the contribution is negative, and so we have rather big axial magnetic anisotropy for this compound. In case of the isothiocyanide,
finalize your lecture, because
yeah, just
2
minutes.
7 minutes over time of your.
Excuse me, 1 minute, Evgeny.
Okay.
Okay, thank you. For the second compound, the d value is also rather high, and the calculation showed even more pronounced d value, which can be seen from the spin orbit calculated the energy of the lowest Kramer's doublet. It's 180. So we divide by 2, and it is around 90 reverse centimeters. And here we have the possibility to use the Orbach approximation for the barrier, and the effective barrier here is around 25 reverse centimeters, because also this is the field-induced value due to interactions in the side. And here, to sum up the comparison of 2 compounds, we have the energy of the first excitation in case of thiocyanide is much less than in case of fluoride, and this is leading to greater barrier for the reverse of the excitation. So, and just a second. So I'm finalizing my work. Some contributions. So I want to thank my colleagues who participated in this job. The synthetic was done by Dr. Yulia Tupolova and Leonid Popov, and the X-ray study and magnetic field properties measurements were done in Chernogolovka by Sergey Aldoshin, Denis Korchagin, Roman Morgunov, Andrei Pali. Thank you them for their support and collaboration. And the research was supported by the Ministry of Higher Education of Russian Federation. So excuse me for taking the time. I'm finished.
Thank you very much, Igor, for your nice presentation. Unfortunately, we don't have time for question. Thank you again. So now, colleagues, we have a break. So we will start at 15:40. 15:40. Please remember. I will write it in chat.